Ever wonder what really makes the digital world tech? You know, how everything moves so fluidly? Well, today we're pulling back the curtain on the beautiful and honestly pretty powerful math that's behind it all. We're talking about geometric transformations.
Yeah, think about it. How do characters in video games or movies move so perfectly? The secret? It's not magic, it's actually math. Specifically, it's this super elegant geometry that tells every pixel exactly where to go for every single jump, turn, and flip you see on your screen.
So, here's the cool part. At the heart of all that super complex motion, there are really just four basic moves, four fundamental transformations. You can almost think of them like the ABCs of movement. And once you get these down, you can basically write the entire language of animation.
Okay, let's start with the easiest one, which is called translation. Really, it's just a simple slide. Picture a car driving down a perfectly straight road. It's not turning, it's not spinning, it's just moving from point A to point B, keeping its direction the whole time.
And here's what that looks like on a graph. See that arrow labeled V? That's something called a vector. Think of it like a set of instructions. It just tells us how far to move and in what direction. And notice this. Every single point on that shape, from A to A prime, B to B prime, C to C prime, they all follow that exact same instruction.
Right, so that's the key thing to remember about translation. The shape saws, its orientation, its form, none of that changes. It's the exact same object, it's just, in a new spot.
All right, next up we have rotation. And this one is pretty much exactly what it sounds like. It's a turn. So this penguin here isn't sliding anywhere. Nope, it's spinning around a fixed point, kind of like a planet orbiting the sun. And this graph shows perfectly how it works. You've got this point P, and it's rotating 90 degrees counterclockwise around that center point. Oh, the key here is that the distance from the center never changes. It just sweeps out that 90-degree arc to its new position.
So you see the difference, right? In a translation, everything moves. But with a rotation, that center point is like an anchor. It stays completely still while everything else just pivots around it.
Okay, so what about a flip? Well, in geometry, we call this a reflection. And the best way to think about it is like a perfect mirror image. You can see it here, right? The clover on the right is a perfect mirror version of the one on the left, flipped right across that center line. Now, on the coordinate plane, this gets really precise. The whole shape here is being reflected across that diagonal line y equals x. And check this out. If you look at point E and its reflection, E prime, that line of reflection slices the segment connecting them exactly in half and at a perfect right angle. And that's true for every single point on the shape. It's really cool.
So the big idea with reflection is that line. That's the mirror. And it's what determines exactly where the flipped image is going to end up.
And for our last one, what if you want to resize something, make it bigger or smaller? Well, that's where dilation comes in.
And back on the coordinate plane, we can be super precise about this. This particular dilation uses what's called a scale factor of 2. That just means the new, bigger triangle is exactly twice the size of the original. And if you look closely, each of its corners is now twice as far from the center point as the original corners were.
Now, this is a really important distinction. Dilation is the only one of these four moves that actually changes the size of the object. The other three, translation, rotation, and reflection, we call those rigid motions because the object itself stays, well, rigid. Same size, same shape.
Okay, so seeing these moves on a graph is one thing, and it's great for understanding them. But how does a computer actually do it? A computer can't see a picture, right? It needs instructions. And that's where algebra comes into the picture.
And this is where it gets so cool and elegant. Remember that vector that was telling the triangle where to go? It was basically an instruction to move 3 units over and 2 units up. So for a computer to move any point, x, y, all it has to do is calculate x plus 3, y plus 2. That's it. Simple addition. That is the entire instruction. Rotation has its own little algebraic trick too. For that 90-degree counterclockwise turn we saw, the rule is you take your point xy and you turn it into negative yx. So you swap the coordinates and you flip the sign on one of them. And that simple rule gives you a perfect rotation every single time.
And what about that mirror flip across the line y equals x? The rule for that is, it's almost ridiculously simple. A point x, y just becomes y, x. The coordinates literally just trade places. It's such a perfect example of how the geometry of the flip is deeply, deeply connected to the algebra.
And for our dilation,
To make that triangle twice as big, the rule was just simple multiplication. You take every single point, x comma y, and you turn it into 2 times x, 2 times y. And that one little instruction scales the whole object perfectly.
Okay, so those rules are fantastic for nice, clean numbers, like 90 degrees. But what happens if you want to rotate something by, I don't know, 37.5 degrees? We're going to need a more powerful tool for that. We need kind of a master key.
Right, the simple rules for 90 or 180 degrees just aren't going to cut it. We need a master key that works for any angle. How do we write a single rule that can handle every possible rotation? This is exactly the kind of problem engineers and animators have to solve every single day.
And here it is. This is the solution, and it is just breathtakingly elegant. It's called the rotation matrix. Now, I know, it might look a little intimidating at first, but the idea behind it is actually pretty simple. You take your point's coordinates, x and y. You plug whatever angle you want into those theta spots, and this little mathematical machine spits out the new, perfectly rotated coordinates for you.
Don't believe me? Let's test it out. If we plug 90 degrees into our master key, well, the cosine of 90 degrees is 0 and the sine of 90 is 1. When you plug those in, the whole matrix simplifies, and guess what rule pops out? xy becomes negative yx. It's the exact same simple rule we learned before. See? This matrix really is the universal key for any rotation. So let's bring this all back home. We started by wondering how those amazing animations work. And now we know. It's not actual magic, but it feels like a kind of mathematical magic, doesn't it?
And really, this is the main takeaway. Geometry is what you see on the screen. Algebra is how the computer actually does it. Every smooth animation, every special effect, every single movement you see, it's all a perfect partnership. We see the geometry, the slide, the turn, the flip, but under the hood, the computer is just crunching millions of simple algebraic rules just like the ones we saw.
So the question is, what other parts of our digital world are secretly being shaped by just these 4 simple moves? I mean, from the user interface on your phone to the way a website is designed, these transformations are absolutely everywhere. So next time you see something move on a screen, maybe, just maybe, you'll see the math hiding behind the magic.